Quality control is a set of procedures that use statistics to detect and solve problems. Statistics are useful because many of the things that happen at a job site happen purely by chance. In quality control, it is important to determine whether something that appears to cause problems is a one-time only accident or regular occurrence. Say you found some money lying on the ground in a certain spot. Because you found money there once doesn't mean you will find anything if you go back to look every day. In the same way, improvements in quality are not the result of tackling an accidental happening. You can determine which events happen by chance by collecting and averaging a large body of data. You know that the areas that need improvement lie elsewhere. Useful though statistics are, many people are put off by their reputation for difficulty. Quality control is a joint effort of all the people working at a job site. Any method of problem solving that is too hard to learn will not be of much help. The simple tools devised for use in quality control are so easy to master that anyone can use them. Japanese have from ancient times been adept at simplifying difficult systems. The kanji, Chinese characters, used in writing Japanese are difficult to learn. Hundreds must be memorized for practical use, but the Japanese long ago came up with a simple syllabary based on these Chinese characters. Anyone who can memorize just 48 characters was able to write anything using this new system. What we QC experts have done with statistics is much like what the ancient Japanese did with kanji. We have broken down a very difficult discipline into a number of simple tools. This is an automobile radio factory. The young women who work in this plant wanted to reduce problems in the manufacturing process. The radios made in the plant are of the familiar push-button type. First, the factory workers collected data on the kinds of defects that occurred. They then tried making a graph with this data, and this is what they came up with. As you can see, a large number of defects were occurring in the area shown at the left. This tells us that the most commonly occurring defect was loose volume knobs. If this problem alone were solved, over half of the plant's defects would be eliminated. We can tell this by simply glancing at the graph, and we call this kind of chart a Pareto diagram. Next, the factory workers got together in a group and tried to think up reasons why a volume knob might loosen and come off. In some instances, of course, the knobs falling off might be linked to human error, or it could be that the original design was bad. In any case, the women mentioned everything they could think of. Their next task was to organize the data. It was ultimately transferred to a diagram of the type you see here. We call this a cause and effect diagram. As you can see, the nature of the defect, in this case loose volume knobs, is written at the far right of the diagram. The next step in filling in the diagram was to list all the causal factors that came to mind. Some of these involved operations and others materials. So major categories of causal factors were created using these and other headings. Each causal factor in the finished diagram was then examined, and the women finally found the answer they were looking for. There is a deep groove-like opening through the middle of the shaft onto which the radio volume knob is pressed. As you can see from this chart, this aperture must be widened before the volume knob can be attached. In the past, this was done using an ordinary screwdriver of the type you see here. As this sidewise view shows, the tip of this conventional screwdriver is beveled. If this screwdriver is not handled properly, the volume knob will not attach securely to the shaft and could easily fall off. It was decided then to develop an improved type of tool with a flat tip that would not cause the aperture to widen too much. Use of this new implement would eliminate inconsistency in the firmness with which the volume knob held to the shaft. When the factory women actually changed this facet of the assembly process, they found, as expected, that the number of loose volume knobs was greatly decreased. They then gathered data on the rate of defects occurring when the new type of screwdriver was used. These data were plotted in a graph together with data on defects before the improved screwdriver was introduced. As you can see, the rate of defects before the new type screwdriver was introduced was 2.2%, meaning that about 2 out of 100 radios produced had knobs that loosened and fell off. Once the assembly process was improved, through use of a new kind of screwdriver, the incidence of defects decreased dramatically to 0.5%. In other words, volume knobs loosen and come off only about 1/4 as many times as before. I would like you all to note carefully that there are usually a variety of reasons for each problem that occurs in the workplace. Many different factors must be analyzed in order to get at the principal causes. But you will find that it is easier to get a grip on any problem when all related data is neatly arranged in graphic form. We have already seen 3 examples of the several forms of graphic representation that are known as the tools of QC.
The Pareto diagram is one of the most often used of the main tools of QC. It is a tool that is indispensable in singling out important problems. Let's take a look at how Pareto diagrams are used.
The QC troubleshooter always makes Pareto diagrams even if he uses no other QC tool. Pareto diagrams help determine what to aim at, how to approach the problem. Let's take a look at this chart, for example. Here you see a Pareto diagram prepared by a camera manufacturer who wanted to reduce overall costs. This particular company uses about 400 parts in producing cameras, each of which contributes to the overall cost. The people in charge first created a graph showing all the parts in descending order of cost. When it was complete, they could see the whole picture clearly. It came as no surprise, of course, that the most expensive part was the body of the camera. Next in line, however, were the prism and the rangefinder cap. Adding up the costs for these 3 components alone, the camera maker found that they accounted for almost half of the total cost of the camera. This being the case, cost-cutting efforts focusing on these 3 components alone could be expected to have a major effect upon the camera's overall cost. The manufacturer thus decided to begin its cost-cutting program here. When we get together to discuss the causes of problems found in the factory, a number of different factors can usually be identified. The difficult part is knowing at which point to begin a program of improvement. If you err in selecting your point of departure, you can go to all the trouble of solving one problem, only to find that the effect on the overall situation is minor. No significant improvement can result in such cases.
A Pareto diagram is a type of bar graph where data on defects, complaints or accidents are collected and classified according to type of problem or type of cause. They are then presented in a bar graph that represents the frequency of problems or the total loss in cash terms resulting from each problem in descending order of magnitude. The Pareto diagram tells us where we ought to begin to make changes for quality improvement and how effective those changes will be. In other words, what we can expect as a result.
The Pareto diagrams that you are about to see were made to illustrate how the women employees of a certain factory spend their pocket money. Patterns of spending, of course, differ from person to person, and this is clearly demonstrated in the charts. The diagram you see here represents the spending habits of a woman who spends most of her money on food. There are many other types. As you see here, certain women spend a great deal of money going to the movies or theatre. Spending patterns depend upon the tastes and preferences of the individual, and it is difficult to control or strike a balance in personal spending. Nevertheless, I think you can see that these diagrams are extremely useful in getting some idea of the nature of their spending habits. Next, let's look at what happened when a factory making motors to order decided to introduce a QC program. Since this factory was not a mass producer, the manager did not think that the usual principles of QC could be applied to his factory, and was not very enthusiastic at the outset. Of course, it was true that the plant was not making enough products to allow for the collection of a large body of data. Nevertheless, the company's QC experts decided to go ahead and create a Pareto diagram and see what they could come up with. And so they made a Pareto diagram showing the causal factors contributing to defects. It was then that they made a surprising discovery. Here is the Pareto diagram the company's QC experts came up with. Looking at this, we see that the biggest cause of defects in this factory was draftsman error. If there is something wrong with the blueprint, the products made from it will naturally be defective. The next biggest causal factor turned out to be inadequate planning, followed by order mix-ups. These three problems alone were responsible for over half of all the factory's defects. When the QC experts stopped to think, they realized that human error was behind all these defects. They found that the same few people seemed to be making all of the mistakes. These few error makers are represented here in the chart as Mr. Mistake, Miss Mistake, and Mrs. Mistake. These particular employees were then singled out for special retraining. In this way, it was possible to reduce the incidence of these causal factors by a very wide margin, and the number of defects was reduced by about 2/3. All this thanks to the Pareto diagram.
Now let's learn how to draw up and read a Pareto diagram, using as an example a graph of noise-related defects emerging from the radio assembly process. First, you decide upon how and for how long you are going to collect data. Before proceeding, you classify categories of problems or causal factors in the way that lends itself most readily to action. Make the term for data collection a workable period, like 1 week or 1 month. Record the frequency of occurrence for each item and arrange the items in descending order according to incidence. Calculate a set of cumulative figures, beginning with the items with the highest frequency of occurrence and adding on. Put your Others category of items at the end, that is, at the far right. Draw a bar graph, beginning at the far left with the item having the highest frequency. Make all the bars of the same width. Make the vertical and horizontal axes of approximately the same length, so that the Pareto graph will form a rough square. Next, draw in a cumulative curve, using the cumulative figures calculated, in a broken line starting from 0 to the upper right-hand corner of the first bar, and all other points intersecting with extensions of the right-hand sides of the other bars. Draw a second vertical axis at the right-hand edge of the bar graph and mark the point where it intersects with the cumulative curve 100%. Lastly, entitle the Pareto diagram and write in any other necessary information, such as the time at which the data was collected or a grand total for the data. By looking at this completed Pareto diagram, we can tell that rotation is the most troublesome noise-related defect in this factory. If the maker of the radios wanted to reduce assembly process defects by half, he would locate the 50% mark on the vertical axis and follow it to the left until it intersected with the cumulative curve. He would then find that over half of all defects could be eliminated by doing away with the problem of rotation. If he sought to reduce defects by 80%, he could tell from a glance at the Pareto diagram that the top 3 problems, rotation, noise and cracking, would have to be solved to do so. Collect as much data as possible. Classify your items in terms of type of problem and/or causal factor. Whenever possible, make the left vertical axis represent cost in cash terms. Try several approaches using different methods of classification. A cause and effect diagram is a chart used to organize all the causal factors contributing to defects or other problems that can be thought up by QC Circle members. First, let's learn how to use one.
The cause and effect diagram comes into play once we've used the Pareto diagram to figure out where best to begin our program of improvement. Our task is to determine what the causes of the problem are, You will find that a given defect may often be caused by any number of factors. When tracking down causes, it is best to gather together the group of people who have the greatest knowledge of the job site situation. You should then encourage them to think about what could be causing the defect and have them say everything that comes to mind. Don't worry about having too much information. It is important to exhaust the list of possible causes. What's more, we have a very good method available for arranging all this data. You will, however, want to have a blackboard or a big piece of paper prepared so that all of the group suggestions can be recorded. The sight of a written list helps to jog our memories, so be sure to write down every idea that is presented. The next step is to rearrange this data in an orderly fashion, and this is done in creating the cause and effect diagram. This is a cause and effect diagram drawn up at a factory where engines are made. The problem here that requires solution is irregularity in engine revolution. The name of the problem is written at the far right end of the diagram, and the causal factors that the brainstorming group came up with are all written here to the left. As you can see, someone suggested that the jig used in the process was itself defective. Someone else suspected inadequate inspection. Yet another person guessed that the design itself might be at fault. Once again, it doesn't matter how many factors are suggested. Just list them all up. They can later be arranged under categorical headings such as those you see here. Once you've identified the major trouble areas, you can go on to track down the smaller factors that contribute to problems. The final product of these efforts will be a diagram that looks like this. You cannot, of course, expect to solve the problem simply by creating a chart of this type. The diagram is just a tool to help you proceed with the following analysis. You will have to investigate each of the factors appearing in the diagram, collecting data to determine whether each really is a cause of trouble. The most important point in making a cause and effect diagram is to make sure that you have exhausted all the possibilities. If something is missing from your diagram, no one will inquire into that area, and a real source of trouble may be left uncorrected. If the point left out is especially important, you may waste a lot of time following up other minor factors. The cause and effect diagram is usually written out on a piece of paper the size of an open newspaper and posted in the workplace where everyone can see it. Oddly enough, you will find that people tend to remember things they had forgotten when they see a visual display of information. This is why we go to the trouble of making cause and effect diagrams. You will find them very effective in helping to track down the causal factors of a problem.
The cause and effect diagram is a written chart that uses arrows to indicate the relationship between the effects that are the result of work and the causal factors that bring about those effects. The cause and effect diagram aims to bring to light all the factors that contribute to the occurrence of a certain problem. It can also give some indication of how to counter significant factors.
This cause and effect diagram gives some clues as to how to cut utilities expenses. Bills for gas, electricity and water combine to make up the utilities cost. The brainstorming group was asked to think up factors that might be keeping these expenses high. All their suggestions were entered in the diagram under the proper headings. This alone does not tell us where we ought to begin taking action to improve the situation. To figure out which problem should be tackled first, we can use these basic categories to create a Pareto diagram. Here is the Pareto diagram made to illustrate utility costs. The biggest chunk of the utility bill goes to pay for electricity. If we itemize the electric bill and examine each of its components, we find that there are some areas where there is room for improvement and others where there is not. By taking action on the remediable points, it should be possible to reduce the overall household budget. Now let's learn how to prepare a cause and effect diagram. The example diagram will help us figure out how to spend less on gas, electricity and water. The word effect in the term cause and effect diagram refers to any of the problems that can arise as byproducts of work. A cause is a causal factor that has some influence upon the result of the work process. The cause and effect diagram is sometimes referred to as a fishbone. The broad arrow that runs through the center of the diagram forms the backbone of the fish,
There are also progressively smaller types of arrows branching off from the backbone and from each other. All of these stand for causal factors. When drawing a cause and effect diagram, first clarify the overall goal of the diagram and then determine and name the effect. The backbone is drawn in through the center, pointing to the effect at the right. Major categories of causes appear in the diagram as big bones. These function as headings for more specific factors. Write in medium-sized and small-sized bones, representing the causal factors that come under the more general factors depicted as big bones. It is important to make the smallest bones specific enough that concrete action can be taken on these factors. When the diagram is completed, look it over carefully to make sure that nothing has been omitted and no factor appears more than once. Scrutinizing the entire diagram, decide which of the factors written down are the most important and circle them in red. Have the entire brainstorming group decide, based on past experience and the existing level of technology, or use data and Pareto diagrams to help you arrive at a decision. Use brainstorming sessions to good effect. Consider the facts carefully. Make an exhaustive search for causal factors.